For years, the Raspberry Pi single-board computer has provided makers and computer enthusiasts a simple, cheap way to connect their electronics projects to the internet. And over that time, the Raspberry Pi Foundation has continually improved their initial design with faster, more powerful components. However, their most recent model, the Raspberry Pi 4, introduced a new challenge. While previous models could perform any task without overheating, the Pi 4 quickly reaches unsafe temperatures when performing strenuous tasks. In this video, we'll look at several ways to cool the Raspberry Pi 4 and see which performs best. Today, we'll measure the CPU temperature of the Raspberry Pi at full load using several cooling configurations. We'll use the same heatsink and 5-volt fan for each test, and use the same stress test in each run. We'll be testing three factors that influence CPU temperature at full load: fan speed, controlled by using either the 3.3 volt or 5 volt rail to power a fan; case pressure, controlled by setting the fan either to push air out of the case or to bring air into the case; and airflow, which we'll control by using both the lid that came with our case and a mock-up lid with a larger hole above the fan. Each test will run for 7 minutes with a 5-minute cooldown afterwards, allowing the CPU to reach its maximum temperature by the end of each test, returning to its idle temperature before the next test begins. With 5 runs for each of the 8 configurations, we should be able to accurately determine which changes resulted in lower CPU temperatures. In order to avoid lurking variables, I started testing with a fresh installation of Raspbian, the Raspberry Pi's default operating system, loaded only with S2, the program performing our stress tests. The Raspberry Pi sat in the same location and used the same power supply, but since testing took around 8 hours to complete, I ran trials over 2 days, with all trials using the stock lid on the first day and all trials using the high airflow lid on the second. Ambient temperature was between 1 and 2 degrees higher on the second day than on the first, meaning that the mock-up case lid may change CPU temperature more than our testing revealed. However, this lurking difference would not change the results of any of our tests. After about 8 hours of testing, the results seemed fairly straightforward. Changing each of our 3 variables made a clear difference in maximum CPU temperatures, with configurations using lower fan speed, case pressure, and airflow performing much worse than configurations using higher fan speed, case pressure, and airflow. However, a 3-factor design of experiment, or DOE analysis, and a few 2-sample t-tests will allow us to test our suspicions. First, for the 3-factor DOE analysis. This analysis allows us to visualize our data using a cube plot with data from each configuration at separate corners. The X, Y, and Z axes represent fan speed, case pressure, and airflow respectively, each at either their low or high levels as denoted on the plot. The main effect of each factor shows the average temperature change created by moving from low to high level for that factor. As you can see, case pressure, controlled by the orientation of the fan, caused the greatest temperature drop of 6.5 degrees Celsius, followed by fan speed, which created an average temperature drop of 5.9 degrees when the fan speed went from low to high. Finally, airflow caused the lowest temperature change, which the move from standard case lid to our more open design, causing a smaller but still significant decrease in CPU temperature of 4.7 degrees Celsius. DOE analysis also reveals any two-way interactions between variables, but in this case none of our two-way relationships appear very strong. The strongest relationship is between pressure and airflow, but similar pressure and airflow levels only produced a temperature 0.36 degrees higher than different pressure and airflow levels. This interaction plot to the right also shows almost no interaction, with all 3 graphs showing no change in slope when the 3rd variable is changed. With initial DOE analysis complete, let's take a look at the effect of each variable individually, this time using 3 2-sample t-tests. In each test, we'll take the ideal configuration and change one variable, using the one-tailed testing feature of the HP50G graphing calculator to compute our critical and testing values for t. As you can see, using a null hypothesis of equality and an alternative hypothesis of a temperature drop between the variables low and high level, each test statistic is significantly higher than the critical statistic for 99% confidence, allowing us to reject our null hypothesis of equality and accept the alternatives. Our variables have a credible impact on the CPU temperature at full load. Finally, one trend in the data stood out to me. It appeared that for each case lid, the temperature at low speed and high pressure was quite similar to the temperature at high speed and low pressure. To confirm my suspicions, I ran 2 more 2-sample hypothesis tests, one with data from low airflow configurations and the other with data from high airflow configurations. As you can see in the overlay, the results weren't quite as expected. With the stock case lid, the test results contradicted my null hypothesis that the 2 configurations yielded equal temperatures, but with the more open case lid, my null hypothesis was not rejected, meaning that the 2 configurations may very well yield similar results. In conclusion, all three of the variables we tested, fan speed, case pressure, and airflow, significantly affect the maximum CPU temperature of the Raspberry Pi. In order to achieve the best possible cooling, the fan must run at its maximum speed, pulling air into the case, and the fan opening in the case must not obstruct airflow through the fan and into the case. However, if near-silent operation or low power draw are required, running the fan as an intake with a high airflow case but from the 3.3 volt rail instead of the 5 volt rail will result in thermal performance better than in any configuration without a 5 volt intake. Thank you for coming on this adventure with me. I hope you learned something new. Have a great day.